So let us take a different topic now, which is electronic devices, what we are having in our syllabus. When we are talking about this topic, electronic devices, what are the important features one should have in memory? The very first concept is, what are intrinsic and extrinsic semiconductors we have to recollect. The pure semiconductors and impure semiconductors. In extrinsic semiconductors, while studying that part, one should recollect what is N-type semiconductor and what is a P-type semiconductor. For that also you people all know pretty well. When we dope that semiconductor, an intrinsic semiconductor, with a third group element, trivalent element, then we people used to get P-type semiconductor there. When we are doping that one with a pentavalent impurity, then we be getting N-type semiconductor there. So what are the major carriers and minor carriers in these two? Major charge carriers in N-type semiconductor are free electrons, whereas in P-type semiconductor are holes. And minor charge carriers in the case of N-type semiconductor are holes, and in the case of P-type semiconductor are electrons. And after completing this part of it, what is the construction of PN junction diode? And what is forward bias and what is reverse bias? What is avalanche voltage and what is knee voltage? These are the areas one has to recollect. And of course, we all know in brief, PN junction diode that works very effectively only in forward biased condition. It doesn't function in the reverse biasing condition, we know that one well. And at the same time, we people all know very well that same PN junction diode is going to be used as a rectifier. A half wave rectifier, a full wave rectifier, like that, two different rectifiers you might have discussed. So in rectification process, we people used to take up a PN junction diode directly. And again, in addition to this, when we consider this PN junction diode, which is a highly doped one, that is what we used to take it as Zener diode. Now a highly doped PN junction diode, we call that one as Zener diode, and Zener diode characteristic curves and other things like you people have already worked out. Those concepts we should recollect back to memory. After completing this part of PN junction diode and even Zener diode, we have to take up the concept of transistors. And transistor, of course, when we consider PNP transistor and NPN transistor, once again major charge carriers in PNP are holes, in NPN are electrons. Minority carriers means the other way. In PNP, they are electrons, and in NPN, they are holes. That is the concept. And while discussing about characteristic curves of a transistor, you need to recollect three different configurations. One is common base configuration, common emitter configuration, and common collector configuration as such. And in addition to this, how this PNP transistor or NPN transistor that works as an amplifier. Followed. This actually is the concept what you have read under transistors as such. Come to the next one. What is amplification factor in the case of a transistor like? Those areas you have to recollect. Then we people are having gates, logical gates. Logic gates we call them. One OR gate, AND gate, NOT gate. Then combinations like NAND gate, NOR gate. Like that XOR gate. All these gates, like of course you people have worked out with their corresponding features. All those concepts you need to recollect once again while discussing this particular chapter, electronic devices as such. So, considering different cases of this particular chapter, the important most aspects of this particular chapter, considering those things into account, we are going to discuss few problems based on different formulae what we people have come across in this chapter. While taking up each and every problem, whatever the relevant theory we just require there, we are going to discuss that theory then and there itself while discussing that model. So, these are the areas one has to recollect before starting this topic, that is electronic devices. And of course, many number of times at JEE level, he has given problems on transistors. Transistor problem, of course, several times he has given. So, every point out of it is important for us. We have to deal with every aspect of that particular chapter in a detailed way. Let us now proceed with the problems. Taking each and every model, I will explain you the relevant theory then and there itself, as I said earlier. So, let us start the first problem. Let us go for the first problem. In a PN junction, the depletion region is 400 nanometer wide and an electric field of 5 into 10 power 5 volt per meter exists in it. That means, in that particular depletion layer, the electric field what is existing, he has given us 5 into 10 power 5 volt per meter as such. The minimum energy of conduction electron which can diffuse from N side to P side is how much? And of course, he has given the options this way. The first option has 4 electron volt, second option has 5 electron volt, third option has 0.4 electron volt, and fourth option has 0.2 electron volt as such. Let us first of all think of this particular model can be worked out based on the basic equations what we have discussed way back in the chapter called electrostatics. Now, if you look at carefully, the distance over here that has been given, the distance that of course we can say that is the thickness in this particular case, thickness of depletion layer, thickness of depletion layer, that is given as 400 millimeter. You definitely can understand that value. So, you can directly write, look at the value given over there. The thickness of the depletion region is given 400 nanometer. Remember this wording, nanometer, that you can all understand 400 into 10 to the power minus 9 meter. That is the thickness of it, very thin, nano, observe that point. What is the electric field across that particular region given? It is given 5 into 10 to the power 5 volt per meter. That is the electric field that has been provided to us. Now, his question is, what will be the minimum energy of a conduction electron which can diffuse from N side to P side? That is the concept. So, you all can understand well, energy is equal to electron charge into potential difference. You can all understand this value. You can write that one as joule. If E is the charge on the electron which is being diffused there, and V is the potential difference across that particular region, then you can understand EV joule will now give us the total energy or the minimum amount of energy what this electron is going to have while being diffused across the system of that particular layer. So you can now write this one, E times V can be written as E into D. These many joule we will be getting. You can certainly understand in this particular case what is the value of E given. It is 400 into 10 power minus 9 into the thickness that is given 400 into 10 power minus 9 into the value of E that is given 5 into 10 to the power 5. Actually, into electron charge joule we people are getting. But all of us we know very well, 1 electron volt is electron charge number of joule. Therefore, we can rewrite the same this way, 400 into 10 power minus 9 into 5 into 10 to the power 5 electron volt. Directly you can write it. So simplify this one now, 10 power 5, 10 power 6, 10 power 7. Now this becomes 10 power minus 2. So overall you be getting 0.2 electron volt. That now must be the corresponding energy of that diffused electron across that depletion region. So what we should understand here, you look at, first option is given 4 electron volt, second option is given 5 electron volt, third option is 0.4 electron volt, and fourth option is given 0.2 electron volt. So whatever is the calculated value we have got here, that is exactly in coincidence with the fourth option which has been provided to us in the problem. Therefore, we can say the correct answer is going to be D here. So only thing you should understand in this case is, if the thickness of the depletion layer is given to us and electric field across the depletion region is given to us, then the potential difference existing across that region is equal to E times D. That only we have taken up in this formula, and we have simplified that one, and the answer we are expecting in terms of electron volt. Therefore, I have converted that one over here. 1 electron volt is 1.6 into 10 power minus 19 joule. That conversion every one of us we know. So that is the conversion what I have taken up to get the value of energy of that electron in terms of electron volt. So 0.2 electron volt, the correct answer, which is D. That is the correct option for us. Check the second problem now. The reverse bias in a junction diode is changed from 5 volt to 15 volt. Then the value of current changes from 38 microampere to 88 microampere as such. 38 microampere to 88 microampere is the change in current that has been observed when the potential difference is changed from 5 volt to 15 volt. The resistance of the junction diode will be how much? The options are given this way. The first option is 4 into 10 power 5 ohm. Second option is 3 into 10 power 5 ohm. Third option is 2 into 10 to the power 5 ohm. And fourth option is 10 power 6 ohm as such. One thing you should understand, whether it is in forward biasing or in reverse biasing. First of all, try to recollect. If I consider this one the PN junction diode, this one is the depletion region, whatever we have. This is P, this is N. If I connect negative terminal of the cell to P and positive terminal of the cell to N, this is called reverse biasing. If I connect positive to P and negative to N, then that is called forward biasing, we know. Whether it is in forward biasing or in reverse biasing, whenever he asks you the resistance of the junction diode, go by the application of Ohm's law straight away. We know very well V is IR. R is equal to V by I. Now here the resistance can be taken as change in potential difference by change in current. Delta V by delta I. That is the equation one has to recollect. The change in potential difference here is 10 because it is changing from 5 volt to 15 volt. The difference between these two values is now going to be 10 volt. What about the change in current? 38 microampere to 88 microampere. The difference is now going to be 50 microampere. Micro is 10 power minus 6, we know that. So 0 when I cut it here, 1 by 5, that now becomes 0.2 into 10 power 6. That only we can rewrite it like this as 2 into 10 to the power 5 ohm. This is the resistance of that diode. But all of you should understand in this particular case, reverse biasing whenever we take up, the resistance of that diode increases enormously in that process. Due to that greater value of resistance, current across the junction diode automatically will be reduced. Because we know pretty well resistance and current, they are inversely proportional to one another. Greater the resistance, smaller the value of current across the junction diode. So that is the reason why whenever we people are reversely biasing a PN junction diode, its resistance increases enormously. Not only that, one more point you can remember here itself. What is the resistance of an ideal PN junction diode when it is reversely biased? Ideal PN junction diode, reversely biased, two conditions he has mentioned. What is the resistance? Resistance is going to be infinity. That means no current that is going to be observed across a PN junction diode as such in such case. Suppose if it is in forward biasing, the resistance is 0 almost. Thereby current increases enormously in that case. That is the difference you need to understand. So if you take 2 into 10 power 5 ohm, this option is tallied with C. The third option is tallying with this value what has been calculated by us. So the correct answer for this problem is C, that is problem number 2 for us. In the next problem, that is problem 3, he gave a branch of a circuit. If the diode is an ideal one, the current across the resistor is how much? The options are given this way. 0.1 ampere is the first option, 0.01 ampere is the second option, 1 ampere is the third option, and 0 ampere, no current, that is the fourth option. Look at the branch of the circuit what has been mentioned here. This one is the symbolic representation of a PN junction diode, we all know that. You will be having, this is P side and this one is N side. It is a triangle that is called bar. Bar represents N and triangle, of course, that arrow. We people used to take up this total feature as an arrow. That is P side and this bar is N side. So that is PN junction diode, fine. What he has mentioned here is, this is now connected to a resistor like this of 3 ohm. and this terminal, this end, whatever we have, is having a potential difference of minus 1 volt, and this has got a potential value of minus 4 volt. Observe carefully, this is at a potential minus 1 volt. This is at a potential minus 4 volt. If you just look at this circuit, this branch of the circuit in fact, you can identify P is more negative than N. N is at minus 1 volt and P is at minus 4 volt. So we can understand in this case P is more negative than N. That is what you should understand by look. The moment P is more negative than N, it is understood this implies PN junction diode is reversely biased. You can all understand well, in reverse biased PN junction diode, current will not be there. No current that flows across. So what is the concept he is asking you? What is the current across the resistor? That is the point. So since it is reversely biased, therefore current is going to be 0. So the moment you look at, you can understand everything, identify at what potential this P is existing now. At what potential that N is existing now. N is at minus 1 volt potential and P is at minus 4 volt potential. One should understand that P is more negative than N. That itself is an indication that this total system, that PN junction in particular, is reversely biased. In reverse biasing, it doesn't conduct anything, we know that one very well. Therefore, the value of current across that particular resistor connected there as a 3 ohm resistor, that will be 0. So we can say the current is 0. That means you can see once again the 4 options. 4th option is the correct option now for us. So answer for this one will now be D. That is the point. So a bit of theoretical concept that is needed. You should identify whether that PN junction is in forward biasing or in reverse biasing. Identify that one and decide your answer. That's all. So that is problem number 3. Check the next number, that is 4th problem. A PN junction diode made of silicon has a barrier potential of 0.7 volt. And a current of 20 milliampere passes through the diode when a battery of EMF 3 volt and a resistor, right, are connected to it. A resistor also is connected to that, a battery is also connected to that. Battery's potential difference has been given 3 volt. And barrier potential, that has been given 0.7 volt. Now what are the questions he is asking? The voltage of the resistor, it is in fact the wattage of the resistor and the of the diode are respectively. I read out, the wattage of the resistor and of the diode are. Wattage, very simply you can understand, it is the power he is asking us to calculate. The power of the resistor and of the diode separately we just want. First one, if you look at what is the power of the diode. Whenever we talk about power of the diode, you have to consider the barrier potential in that diode, whatever that is existing. So power in general is going to be voltage into current. We people used to write this one as V into I. That is the general formula. But what is this V to be considered as? It is the barrier potential that is to be taken up. What is the barrier potential that has been given here? It is given as 0.7 volt. Fine. What is the amount of current that is passing through the diode given? 20 milliampere current passes through the diode, he said. So take that value as it is here, 20 milliampere, right? You can directly write this into 10 power minus 3. So if you take here 0 on this point, if you cut it over here, 14 into 10 power minus 3, which now can be written 0.014 watt. 0.014 watt is going to be the power of the diode. But according to the order, what is the question is asking, if you look at second part of the question is power of the diode. I have calculated that one first. So you can identify right away the very first option is going to be the correct value, because if you look at the first option is given 0.044 watt and 0.014 watt. Second option is 4.6 watt and 0.14 watt. Third option is 0.46 watt and 0.14 watt. And fourth option is 46 watt and 14 watt respectively. So second part of the question, when I have solved, almost I can guess that the first option must be correct. But let us calculate even the other one also. What is going to be the power of? He is asking you two questions, right? One is the wattage of the resistor and one is the wattage of the diode. So power of the resistor. Resistor in the sense you should understand the entire circuit is to be taken up now. Entire circuit means what? PN junction diode is there, that's connected in series to a resistance there he is talking about, and across the entire system a cell of potential difference 3 volt that is connected there. So you can directly understand in this particular case what is going to be the power of the resistor. You have been given 3 volt is external PD applied. 0.7 volt is given as the barrier potential. Then what will now be the effective value of potential difference there, please? It now is going to be V into I, no doubt. This V now to be taken as 3 minus 0.7 into current once again is 20 into 10 power minus 3. This now is going to be 2.3 into 20 into 10 power minus 3. 2.3 into 20 is going to be 46 simply. You can directly understand that one. 46 you will be getting. So this now to be taken as 46 into 10 power minus 3, 0.046 watt we will be getting. So one is 0.046 watt and one is 0.014 watt. So both the values have been given in the very first option, 0.046 watt and 0.014 watt is the first option for us. So directly we can take the first option is the correct answer for this. So if you look at the power of the diode and power of the resistor connected over there, he is asking you two questions. The first option is 0.046 watt and 0.014 watt. That particular option is the correct option for us. After calculating this, we get the same values there. So that is the question number 4. Check the problem number 5 now. Assuming the diodes to be ideal, the potential drop across each capacitor would be how much? He has given us a small circuit which has got 2 diodes and 2 capacitors connected, and one cell also has been connected over there across. The options are given this way: 12 volt and 12 volt. Second option is 16 volt and 8 volt. Third option is 0 and 24 volt. And fourth option is 8 volt and 0 volt. Let us first of all draw the circuit what has been provided to us. He has just given us one capacitor connected here and one PN junction diode that is connected like this. And one more PN junction diode is connected over here this way, like this. And here he has given us another capacitor connected this way. This is one capacitor, this is the other capacitor, and here he has given us a cell connected. Whenever such a circuit is given, identify carefully how the cell that has been connected across. Positive is connected to this and negative is connected to this. Identify the connections carefully of the cell what he is talking about. So you can now write this one is C1 given, this one is given as a C2. What are the values he has provided to us? Say C1 is given 4 microfarad and C2 is given 8 microfarad. And here 24 volt that has been given across the cell. Observe those values first of all carefully, because whenever you deal with any problem of a diode, particularly a PN junction diode I am talking about, whether that is in forward biasing or in reverse biasing, identify that one carefully. You can estimate the required values only when the PN junction diode is forward biased. If it is reverse biased by any chance, no current that flows across that one, no value you can estimate over there excepting the resistance. So you can understand in this particular case, look at this PN junction diode. If I take, this is P side, this is N side. This is P side, this is N side for the second one. If I take this as a diode 1 and this as a diode 2, for my rather observation, like for my easiness. Now if you look at carefully, negative is connected to P and positive is connected to N for the second diode. You can understand negative to P, positive to N. That means this is now connected in reverse biasing. When it is in reverse biasing, no current that flows across that particular diode, we know that one very well. Whatever be its value, that is of no use for us. Now look at the other diode as well. If you take positive is connected to P and negative is connected to N, you directly can identify this diode 1 is now in forward bias condition. When this is in forward biasing, current flows. When this is in reverse biasing, no current flows across that particular junction diode. Forget about that. Now you can directly understand this capacitor, both are now in series to this diode and the entire system is in series to this cell. So what we can directly understand is, what is C1 is to C2. You just take 4 and 8, 1 is to 2. What will now be the potential differences across these two capacitors respectively? What is the ratio of the potential differences? V1 is to V2 must be C2 is to C1. Because you all know pretty well, Q is equal to CV formula. When I write, Q remains constant in series sequence. Then V and C are inversely proportional to each other. That is what I have applied over here. So V1 is to V2 now becomes C2 is to C1, which now becomes 2 is to 1 as such. And you can directly understand 2:1 means total 3 parts. 2 parts for the first one, 1 part for the second. As a whole we can take 3 parts like. Therefore, what is V1? That V1 is nothing other than PD across the first capacitor. What will now be V2? V2 is the potential difference across the second capacitor. These two are the values I am calculating now. So you can now understand V1 is equal to 2/3 of the applied voltage. Applied voltage being 24. This now becomes, right, 16 volt. So you can directly understand the first capacitor has got a potential difference of 16 volt across its plates. Now come to the second one, please. What will be V2? It's 1/3 of the applied voltage. That now becomes simply 8 volt as such. So look at this construction now and look at the ratio what we have taken up now. V1 is to V2 is C2 is to C1, which becomes 2:1. 2:1 means total 3 parts. 2 parts out of 3 of the applied voltage should be across the first capacitor. So that now becomes 16 volt and second one automatically becomes 8 volt as such. So 16 and 8 must be our answer. Which answer that is tallied with that? Look at. Second option is given 16 volt and 8 volt respectively. Therefore, we can say the answer for this one as B. That is the point we have to understand. So just identify which PN junction diode is in forward biasing, which PN junction diode is in reverse biasing. The one which is reversely biased, it does not carry any current. No current will be observed across its junction. That is a waste. Now eliminate that, and according to the remaining circuit, you decide the correct answer whatever is required. That is the point to be noted, and this is problem number 5 for us. Check the problem number 6 now. In a half wave rectifier, a PN junction diode with internal resistance 20 ohm is used. If a load resistance of 2 kilo ohm is used in the circuit, then the efficiency of this half wave rectifier is. One should understand first of all what do you mean by efficiency there. Efficiency we write generally as eta. For a half wave rectifier, it is 0.406 RL by RL plus RF. Observe what is what out of that one. This RL, we call this one as load resistance across which the output is going to be taken up. And what is this RF now? It is forward resistance of PN diode, that is PN junction diode. You should understand forward resistance means when PN junction diode is in forward biasing. What is the resistance value corresponding to that? That is what actually we call it as RF. Now what are the options given? 80.4%, second option 40.2%, third option 20% and fourth option 50%. Look at this equation first of all, and what are the values given? You just identify. Load resistance is given 2 kilo ohm. So eta can be written as 0.406. 2 kilo, 2000 by this RL is 2000 and this value is 20. So directly you can write this value as 812 over 2020. But he is asking you the percentage. Percentage means what is to be done we all know very well. You just multiply this whole thing by 100. So if you simplify this total lot, you will be getting around 40.2%. That 40.2%, whatever we people are obtaining here, that is exactly in accordance with the second option which has been given there. So you can write directly the answer for this one as B. But one thing I just want to mention here, if you look at this calculation carefully, if the diode is an ideal diode, if the diode is an ideal one, RF will be 0, then RL gets cancelled. You are left with 0.406. If you convert that one into percentage, like, you will be getting the value of eta maximum is going to be 40.6%. So according to this formula, half wave rectifier, whenever we consider, the efficiency will not be more than 40.6%. So if your answer is nearby that one, you need not work out anything, you can opt for that. For example, in this particular problem only, first option is above 80, 80.4. Second option is 40.2 and third option is 20 and fourth option is 50. So it cannot be 50, it cannot be 80. So your option must be either B or C. So that you can identify its nearby answer for 40.6, that is 40.2, then automatically we can adopt that particular value as our answer. So for sixth problem, the answer is 40.2%, which of course is tallying with the second option given there in that problem. That is problem 6 what we have. Look at problem number 7 now. This is based on full wave rectification. A full wave PN junction diode rectifier uses a load resistance of 1300 ohm. No filter is used. If the internal resistance of each diode is 9 ohm, the efficiency of this full wave rectifier is how much? That is the question. The options are given 80.64%, second option 40.6%, third option 13.9%, and fourth option is cent percent, 100%. 100% is ruled out. 13.9% is very, very less. So 40.6% usually we will be getting for a half wave rectifier. Certainly more than that one it will be. So 80.64 obviously will be the answer, no doubt. But let us see what is the formula for that. Now you can understand, for a full wave rectifier, percentage of efficiency we can write 0.812 RL by RL plus RF whole multiplied by 100. That is percentage of efficiency. I am writing this, of course, can be taken 81.2 into load resistance mentioned in this problem is 1300 ohm divided by 1309 we can take up as T is the value of RF plus RL. Now each diode has been given with a resistance of 9 ohm. So that into 100 means I have already written that one 81.2 here. So if you simplify this one, you will be getting 80.64%. This option, whatever we people are getting after calculation, that is exactly the first option which has been given there. So we can write directly the answer for this one as A. Once again, you can understand one point from this particular formula, please. If you consider the diode as an ideal one, then RF will be 0, RL gets cancelled. The percentage now becomes 81.2%. So what will now be the maximum percentage of efficiency in the case of a full wave rectifier? 81.2%. It cannot be more than that. That is maximum. So your answer must be near around that value. So even if you remember that point, you can identify the answer very easily in this problem. 80.64% is very close to 81.2. So obviously that will be the value of efficiency, the percentage of efficiency what has been asked in this problem. So the answer for this one is 80.64%, which is the first option for problem number 7. Problem 8 is based on Zener diode. From the circuit, the maximum and minimum values of Zener diode currents are. That is a question. And of course, he has given us a small circuit of Zener diode there. And what are the values given over there? Let us write first. There is a resistance here given. This is 5 kilo ohm. And here is a Zener diode that is connected this way. This is the Zener diode what has been given to us. And of course, we have another resistance that is connected in parallel to this. This value is given 10 kilo ohm. And we know pretty well Zener diode, whenever we draw, that is the symbolic representation. This bar can be written like Z. And here he has just connected 80 volt to 120 volt PD across the system. That means a cell is to be connected in such a way that this is P and this one is N. Negative terminal to P and positive terminal to N is to be connected that way. So we can understand that this is now at positive potential and this is now at negative potential. So Zener diode will make it function very effectively in reverse biasing. In forward bias, generally it will be having the same functioning like an ordinary PN junction diode. And what is the PD across this Zener diode given? It is given as 50 volt. In fact, you can understand potential difference across Zener diode is 50 volt, means potential difference across 10 kilo ohm also will be 50 ohm. And that 50 ohm itself, we should call it as output voltage. That is also called Zener voltage over there. That is the concept what we have to understand there. So what are the options mentioned? Let us see them first. First option says 6 milliampere and 5 milliampere. Second option is 14 milliampere and 5 milliampere. Third option is 9 milliampere and 1 milliampere. And fourth option is 3 milliampere and 2 milliampere respectively. So what is the correct option? We just have to pick up. Look at now, this is 80 volt you take first. When 80 volt is the applied voltage and 50 volt is output voltage. Input is 80, output is 50. 50 across the Zener diode. Then what is across this particular resistance now? It should be 30 volt. Total 30 plus 50 should be equal to this applied voltage. And what we just want is what is the current across this. If I just take the current across this series resistance as I series, and current across this load resistance as I load, then the difference of these two must now be the value of current across the Zener diode. So what is the concept here? Current across series resistance is equal to current across the load resistance plus current across the Zener diode. That is the point. I just want the value of Zener diode current first. IZ I want. I now can write IS minus IL. Current across series resistance minus current across load resistance. That is the point. Now current across series resistance, I is equal to V by R. So we can write 30 by 5 kilo ohm, that is 5000, minus current across the load resistance. What is the PD across this one? 50 by 10,000 ohm. Now you can directly get this calculation. 10,000, if you take LCM here, this becomes 60 minus 50. It is a 10 by 10,000. So 1 by 1000 in the sense we can write 1 milliampere. That is the current what we are getting. That is the current when the input voltage applied across the system is 80 volt. Exactly like that, you calculate for 120 volt also. When input voltage is 120, when this output is 50, 70 volt will now be the PD across the series resistance. This is the value corresponding to 120 volt I am writing. This is the value corresponding to 80 volt I am writing. So what will now be the current across the Zener diode for the second pair of values? I can write IS dash minus IL. This IL remains the same because output will be the same. So what we can understand in this particular case here, this 70 by 5000 minus 50 by 10,000. So this now becomes 9 milliampere as such. Look at these two values, 1 milliampere and 9 milliampere are the corresponding values of currents what he is talking about. If you look at the values given in the options, third option you look at that one, 9 milliampere and 1 milliampere, maximum and minimum currents he is asking. This is now to be called I minimum for us, right? And this now to be called as a current maximum in this particular case. So what is maximum current and minimum current is the question. So maximum current becomes 9 milliampere and minimum current becomes 1 milliampere. Both of course are given in the third option for us. Therefore, the correct answer for this one is going to be C as such. So one thing you should understand before attempting the problem is whether that Zener diode is in reverse biasing or not. Because we people used to make that Zener diode function in reverse biasing more effectively. In forward biasing, it is just like an ordinary PN junction diode, no change whatsoever you find over there. So this is the point we have to understand. So that is problem number 8 what we have in this order. This problem number 9 has been asked in one of the IEEE papers earlier. He gave us 4 separate branches. In each branch, of course, there is a PN junction diode that is connected. Now, his question is this: in the following, the reverse biased diode is, which diode is reversely biased out of the 4 options what he has given us? You need to observe and identify which particular option gives us the reverse biasing of this PN junction diode. Let me just give all the 4 options what have been given to us in the problem. First one, if you look at the first option, that is A, it is given this way. There is a PN junction diode this way. This is P side and this one is N side. and he has connected a small resistor here, and this is the other end of that is the other terminal what he has given us. And resistance, of course, no value has been provided to this, that is said as R. Fine. And our concentration is not on that officially. What are the potentials given at these 2 points? Identify that one carefully. This is given plus 10 volt and this is given plus 5 volt. That is the first option what has been given. Let us decide the answer by taking each and every option one after the other. Look at this option first. This N side is at plus 5 volt. That P side is at plus 10 volt. So you can understand now P is more positive than N. That itself is a wonderful clue for us to say that implies it is forward biasing. In forward biasing, P will definitely be at greater positive value than N in terms of potential. P is more positive than N. So first option is not the correct option for us. Fine. Check the second option now what has been given. Once again a PN junction diode has been mentioned this way. This is N and this one is given as P, and here is again a small resistance that has been connected like this, and the other terminal is shown this way. This is N, this is P, this is of resistance R. But identify the values given here. This is minus 12 volt and this is minus 10 volt. Look at this one, whether this is in reverse biasing or not, we have to decide. By looking to this one, N is at minus 12 volt and P is at minus 10 volt. So you can understand now N is more negative than P. Either P is more positive than N or N is more negative than P, both are one and the same in one way. Even this one also we can say it is in forward biasing. So this also is not going to be the correct option for this particular problem. Now check the third option please. Again he has given us a PN junction diode with a resistance. This is P side, this is N side, there is a resistance connected here and this is one more end there. This terminal is directly connected to the earth like this. This is P, this is N, this is R. Fine. But what is the potential given here? You identify it is now given minus 10 volt. That is the one. Now look at carefully, the moment you are connecting this end directly to earth, what will be the potential at this particular point? 0. So P is at 0 potential, N is at minus 10 volt potential. So we can understand once again N is more negative than P. This is as well same like the second option. So what we can understand, this implies it again is forward biasing. So when you can identify out of 4 options, 3 of them are in forward biasing, then obviously the correct option must be the fourth one. There is no doubt about it. But okay, let us see what he has given for this fourth option as well. This is D I am talking about. Again he has given us a PN junction diode. This is P, this is N. Once again this end is directly connected to the earth. It is earthing terminal. And of course, we people are again having one more resistance here connected and other terminal is given there. What is its potential? You just identify. It is given plus 5 volt. The moment this terminal is connected to earth, we can take the potential over there at that particular end is 0. This P is at 0 volt, N is at plus 5 volt. So, what we should consider here, N is more positive than P. You can certainly understand N more positive means that is definitely in reverse biasing. So, we can say this is the one in which we people are finding reverse biasing of that PN junction diode. So, which is reversely biased is the question. So, A is not the correct option, B is not the correct option, C is not the correct option, then automatically D will be correct, no doubt. But after checking it also, you are observing that N is more positive than P, that itself indicates it is in reverse biasing. So, the correct answer for this particular problem is D now. That is the way we people have to check, and this was the question given in one of the EEE papers earlier. So, that is problem number 9. Check the next number, that is problem 10. If the ratio of the concentration of electrons to that of holes in a semiconductor is 7/5 and the ratio of currents is 7/4, then the ratio of drift velocities is how much? First option is given 5/8, second option 4/5, third option 5/4 and fourth option 4/7. What is the correct option out of it? We have to decide. In fact, he is asking you drift velocity. Drift velocity. In fact, we know drift velocity Vd if I write, it is I by NEA. I being the current, N is a number of electrons which of course are crossing per unit volume of the total conductor. That of course we can call it as concentration of electrons, nothing else. And in addition to that, E is the charge and A is area of cross section of that conductor. So, what can we write now from this? Drift velocity 1 by drift velocity 2 can be written as I1 by I2 into N2 by N1. What is the ratio of currents he has mentioned? 7/4 into what is the ratio of concentrations of electron he has given? 7/5, write that one, 5/7. So, 7 getting cancelled, you now are left with 5/4. So, what will now be the ratio? Drift velocities, they are in the ratio 5:4 according to this. So, 5/4 is supposed to be the correct option for us. That now is the third option in this particular case. That means it is C. So, this is the formula which you have discussed way back in current electricity. From that only we people have considered this solution here. That is problem number 10 for us. Check the next number now. This also has been one of the problems given in IIT papers earlier. In a PN junction diode, a square input signal of 10 volt is applied as shown. Square input signal has been applied across. So, what exactly the input signal he has given? I will show you that one. He just has given this one like this. This is given plus 5 volt and this is given minus 5 volt. That is the input signal which has been fed to that PN junction diode. Which PN junction diode? He has given even that circuit also. This is the PN junction diode he is talking about. And a resistance over here is connected across. This is the circuit what has been given. This is PN junction diode. This is input. In fact, you can understand these two are input terminals, and these two we can consider them as output terminals as such. So, input terminals and output terminals like that he has shown, and this value of resistance generally we call it as a load resistance. Across that load resistance only we people used to extract the output. So, that is actually given. This is the input signal which has been a square signal like that is given to the system, and what is his question there? Then the output signal across load resistance is how much? What is the output signal? That is what he is asking. So, let us first of all check. He has given 4 options. First option is given this way. The way he has mentioned, this is one terminal, this is the other terminal, this is given plus 5 volt. And the second option is given almost the same, but the voltage value has been changed. Like this he has given, this is given plus 10 volt. That is the second option which has been mentioned. And coming to the third option which has been given there, same he has given in the reverse way like this. Same almost, that is given minus 10 volt is given here. That is the third option given. And fourth option D is again given this way, square signal only, right, but this is minus 5 volt he said. This is the first option, the second, third and fourth. PN junction diode he is talking about. The moment he says PN junction diode, everyone should recollect the fact that it works only in forward biasing. It does not function in reverse biasing, we know it. Then if this is the input signal, only half of that signal will come out. We can all understand that is almost like a half wave rectifier. So, what we can understand in this particular case, that to positive peak, that is positive half of the cycle, that is input, that only will come out. So, automatically this must be the correct option for us, because this is 10 volt. Here maximum is 5 only, we cannot get 10. It is not an amplifier circuit. Another thing, that is a negative. This is negative. It doesn't work in reverse biasing at all. So, these two you need not consider them at all. Only among the first and second options you have to pick up the right one. So, what is the correct answer for this? That correct answer for this one is simply A, because the reason is very simple. PN junction diode works only in forward biasing. It does not function in reverse biasing at all. That is the point one has to understand. Check the next number, that is problem 12. A pure silicon crystal of length 0.1 meter and area 10 power minus 4 meter square has mobility of electrons mu e and holes mu h as 0.135 meter square per volt second and 0.048 meter square per volt second respectively. What are the values given? Let us first of all write. Length is given 0.1 meter. That is one value which has been provided to us, and area is given something like 10 power minus 4 meter square. That also is given in meter square only, so no need for us even to convert its value anymore. And what are the mobility values he has provided? Mobility of electrons, that is mu of electrons, that's value is given 0.135. 0.135 what? Meter square per volt second. And what about mobility of holes he has given us? That is 0.048 meter square per again volt second. Fine. And what is the applied voltage he has given us? Just look at that value as well. Applied voltage, that is given to volt. Right. And what is the value of concentration, charge concentration? He has given us 1.5 into 10 power 6 per meter cube. Charge concentration. Charge concentration, that of course we represent it by N. You can understand that one well. It's 1.5 into 10 to the power 6 per meter cube. Per meter cube of, that is per unit volume. Those many number of electrons or holes we people are having. That is the point what one has to understand. Then the total current flowing through the crystal is how much? We just want what is the total amount of current that is flowing through the crystal. And what are the options given? First option, 8.78 into 10 power minus 17 ampere. Second option, 6.25 into 10 power minus 17 ampere. Third option, 7.89 into 10 power minus 17 ampere. And fourth option, 2.456 into 10 power minus 17 ampere. So what is the current that is flowing through the crystal? That value we just want. So what is the formula for current here? It is charge into charge concentration into mobility of electron plus charge concentration of hole into mobility of holes into what next we are having? That area into volume by length. Just observe this equation carefully. Charge into charge concentration, that to electron charge concentration into its mobility, hole concentration into its mobility, into area of cross section what has been given into volume by length. That is actually the formula. But the charge concentration he gave the same. So what can we write now? 1.6 into 10 power minus 19 the charge. 1.5 into 10 to the power 6 the value of concentration into what is mobility given? 0.135 plus 0.048 into the value of area is given 10 power minus 4, right? And in addition to that, V is going to be the voltage that has been applied. How much is the voltage that is applied over there? It's 2 volt. By the length that has been given here, 10 power minus 1 you take. So observe carefully, E into charge concentration into its mobility of electron plus charge concentration into mobility of hole into area of cross section into the potential applied by length. That is the concept. In fact, you people can understand what is this V by L officially. V by L we can write that is nothing other than electric field across the system. Electric field across the system only is represented by this V by L. So this is the calculation what one has to go for. If you simplify this one, you will be getting exactly 8.78 into 10 to the power minus 17 ampere. 8.78 into 10 power minus 17 ampere, which of course tallies with the very first option given in the problem as such. So observe once again carefully. This formula you just have to remember for the total amount of current that is flowing across any crystal when both electrons and holes together are in motion there. In the sense Electron motion and hole motion, of course, that is just opposite to one another, that we know it very well. What is the total amount of current due to both electrons as well as holes in the total system? That's what has been asked here, and the correct answer is this 8.78 into 10 power minus 17 ampere, which tallies with the first option for us, that is problem number 12 what we are having here.